So here we've got two graphs of a wave. And keep in mind, these are graphs of the same wave. Ultimately, we're just looking at one single wave propagating through space. And why would we have two graphs of it? Why is it useful to have two graphs if we're just dealing with one wave?
Because we can only graph like two things on two axes, but the wave, it has X, T, and Y. Yeah,
we're looking at just these two-dimensional graphs. You certainly can make a three-dimensional graph. You could have a Y-axis, an X-axis, and a time axis, but it gets really confusing to try and read. So limiting ourselves to just a two-dimensional graph, we can deal with this function of two variables by looking at cross sections. We can look at all the X values and their corresponding Y values at one instant in time, or we can look at all time values and their corresponding Y values at one location in space. So for the XY graph, we're holding time constant. We're looking at just one single instant in time, but examining the entire shape of the wave. If this is like, maybe we're shaking a rope or something, we're looking at the shape of the rope at that one instant in time. So this is often called a snapshot. Of the wave, in the sense that this literally is like if you took a video of the wave traveling and then pressed pause at time 2 seconds. Then this graph represents the shape of the wave at that instant. Because the Y value just represents how high or low above equilibrium that location is at that time. Whereas the T versus Y graph, we're talking about time passing, but we're only looking at one single location. So I generally think of this one as essentially a history of one single piece of the rope. Like if you imagine tying a ribbon on one part of the rope to market, as the wave travels, that ribbon, that one piece of rope is just oscillating up and down. So this time versus Y graph is a history of what's happening to that one little piece of rope as time passes, but just focusing on that one location, bobbing up and down. Any questions on the meaning of that so far? And as for the terms oscillation and propagation that someone was asking about, oscillation just means that one object, in this case, that one piece of rope, is just moving cyclically. It's moving up and down, up and down, up and down. But on average, it's not really going anywhere. It's just oscillating in place around a constant equilibrium point. So any given individual piece of rope is not moving. There's not moving forward. It's bobbing up and down. Or in a longitudinal wave, maybe the individual objects are oscillating back and forth, but they're not really going anywhere. So if the individual objects are just bobbing up and down or back and forth and not going anywhere, what is traveling here? In a wave, what is actually moving? What's moving along the rope? Yeah, energy is a big part of it. You've got energy being transferred from one end of the rope to the other. If you just got a long rope and you shake one end of it, and this pulse travels through the rope, that pulse is a disturbance that travels and it carries energy with it. I don't know if I'd really say the wave is the energy. I'd say the wave is the disturbance that travels, but that traveling disturbance carries energy with it. And you could also say it carries information with it. Like if you're able to put a pulse into this wave and somebody else is standing at the other end and watching it, you could put in, I mean, even just with simple pulses, you could use Morse code or binary or whatever and send messages through these pulses of waves. So we could say that the wave is this traveling disturbance that carries energy and information with it. We could also think of the information it carries in terms of the properties of the wave. For instance, what are some properties that a wave has that can actually be measured?
Like amplitude?
Yeah, the amplitude. Generally written as capital A. And what does amplitude mean? And wavelength and period, let me write those down also. Wavelength, lambda, period, capital T. So what do these represent? Like what does amplitude actually mean on a wave like this? Yeah, the maximum displacement, how far it can get from equilibrium. In this case, how far above or below equilibrium. So the equilibrium is just the the center here. So we want to know how far above or how far below. And the amplitude should be the same on both graphs because these are just two different images, two different depictions of the same wave, two different viewpoints. So the amplitude should just be one single number. And if you know the equilibrium, you can just measure the distance from equilibrium to the trough or equilibrium up to the crest. In this case, we don't have a value for equilibrium, but we know the distance from lowest y value to highest y value is from 10 to 60, that would be 50. So what would the amplitude have to be here? Yeah, from crest to trough, that vertical displacement is twice the amplitude. So half of that would be the amplitude. Amplitude is 25. Half of the difference between highest and lowest y values. So you could calculate that by just taking the difference between y max and y min and having that. What about the wavelength? What does wavelength mean and how would we find it from these graphs?
It's like the distance between like two peaks, right?
Yeah, if you have like a wave, the distance from peak to peak, crest to crest, is one wavelength. Or alternatively from trough to trough, also one wavelength. Just the distance, the actual physical distance in meters for one full cycle. You could also measure from any point on the wave, but you got to be very careful because, for instance, if you're measuring from equilibrium to the next equilibrium, is that one wavelength? No, that's only, in fact, that's what fraction of a wave or wavelength? Yeah, this is just half a wavelength. You want to go from, and you got to be careful about labeling the points. This isn't just equilibrium, this is specifically equilibrium on the way up. So we want to go until we get to the next point that can be classified as equilibrium on the way out. So this would be one wavelength. If you just go from equilibrium to the very next equilibrium, that's only half a wavelength. Or maybe like equilibrium to the next crest would be a fourth of a wavelength and so on. So you can certainly use that. You can use any recognizable fraction of a wavelength when you're measuring this, but just be careful about what fraction it is. For instance, in this case, do we have 2 points on the graph we can identify that are definitely the same point on one cycle and the next that we can measure the difference between? Are there 2 x values that are definitely exactly one cycle apart?
Wait, I'm sorry, I don't understand what you mean by that.
In the sense of like from a crest to a crest, or from a trough to the next trough, or from equilibrium on the way up to the next equilibrium on the way up. Yeah, it looks like 2 and, yeah?
14.
Yeah, I think 2 and 14 would work here because we have 2 is equilibrium on the way down and 14 is the next equilibrium on the way down. So from 2 to 14, that's how far?
12.
So that should be the wavelength. And formally, these should have units. I haven't really written units on these graphs, but if like x is measured in meters, the wavelength would be 12 meters. And likewise, if y is measured in centimeters, then the amplitude would be 25 centimeters. But these should all have units of measurement attached to them. Also, even if we didn't have the 14 here, like if this was covered up, we could still find the wavelength by using what sort of measurement if we didn't have this 14 here. What's another fraction of the wave that we could measure? We could look for half a wavelength. Yeah, maybe for instance, from 2 to 8. From 2 to 8, that's from equilibrium on the way down to equilibrium on the way back up. That's definitely half of a wavelength. So we could say from 2 to 8, that's 6. So 6 is half a wavelength, Double that, you get 12 for the wavelength. Exactly what we measured here. Or alternatively, maybe from a trough to a crest. From here to here, we've got a trough that looks like 5, a crest at 11. So from low point to high point is 6, from 5 to 11. That's half a wavelength, so you double it, you get 12. Any questions on that so far? So we've got the wavelength and also the period. What does the period mean in this context?
Does it have to do with like time?
Yeah, the T here stands for time, specifically the amount of time, right, the amount of time for one full cycle. So if you, for that, you'd want to look at the time graph, how much time it takes to go, like if you watch just one point as it oscillates, as it goes from trough to crest to trough again. So trough to crest to trough, or crest to trough to crest. That amount of time is one full period, one full cycle worth of time. And you can measure that on the time graph. Same idea as wavelength, but on the time graph instead of the position graph. So if you can measure how much time it takes to go from crest to crest or trough to trough, that's the period. In this one, we don't really have enough of the time axis to measure one full period. But what's a convenient fraction we can use here? What's a convenient pair of points we can measure that's a easily recognizable fraction of a full cycle? From where, or from when to when, I should say, because these are times. Yeah, from 1 to 4, that looks good. If we start at time equals 1 second and go to time equals 4 seconds, that looks like 3 seconds worth of time. So we might say delta time equals 3 seconds. And what fraction of a cycle is that? Yeah, if you're going from equilibrium on the way up to the crest to equilibrium on the way down, that's exactly half of a cycle. So we can say that's half of a period. And then how did you solve for period there?
Divide by a half.
Yeah, divide by 1/2 or multiply by 2, same thing. So we double both sides, we get period is 6 seconds. That would be the period for this wave, 6 seconds. I'm gonna go ahead and fill in units here. Let's assume that X is measured in meters. Time is measured in seconds, and Y is measured in, let's say, centimeters. So the amplitude, being a Y distance, is going to be in centimeters. Same units as Y. The wavelength has the same units as X, and the period has the same units as time. Also, frequency is basically the same concept, except how do we define frequency?
It's like 1 over period.
Yeah, frequency is the exact reciprocal of period. So that'll be 1 over 6. And the units, what would the units be for frequency here?
Hertz.
Hertz, which really just means 1 over seconds. Hertz means, it's probably best to interpret it as cycles per second. So for instance, 10 Hertz means 10 cycles happen every second. 1/6 Hertz means 1/6 of a cycle happens every second. If you look at, let's say, 1 second worth of time, from here to here, from 1 second to 2 seconds is 1/6 of a cycle. So 1/6 of a cycle happens per second, or to put it another way, it takes 6 seconds for one full cycle to happen. A useful way to consider the distinction between these is that the period is seconds, per cycle, And the frequency is cycles per second. Period is how many seconds it takes for one full cycle to happen. Frequency is how many cycles happen each second. So they're very closely related ideas. They're essentially the same information. They're just reciprocals of each other. Period is 1 over frequency. Frequency is 1 over period. Any questions on that so far? Also tied together in a very interesting way. If we multiply these, if you multiply together wavelength times frequency, wavelength is really just meter. I mean, we measure it in meters, but it's really meters per cycle, the number of meters, the distance in one full cycle. So wavelength is meters per cycle. Frequency is measured in hertz, which is cycles per second. If you multiply those units together, what happens to them?
Cycles cancel.
Yeah, cycles cancel out, giving rise to meters per second, which is the usual measurement of, yeah, that's speed. This is why wavelength times frequency tells you the speed. Not the speed of the individual rope pieces moving up and down, but the speed of the wave propagating forward. The wave travels forward at a certain speed, and that speed is always going to equal the wavelength of the wave times the frequency of the wave. Because when you multiply those, cycles and cycles cancel out, you get distance over time. And that's the definition of speed. You could also write that, instead of writing it as times frequency, you could write it as divided by period. Wavelength divided by period. Because multiplying by frequency and dividing by period are the same thing. And this makes it, I think, even more clear that speed, we usually define speed as distance over time. Wavelength is a distance for one full cycle. Period is a time for one full cycle. So this really is a distance over a time. Any questions on that so far? Yes, I'll be posting the recordings on YouTube and linking to them on math.ngs.org. So in this case, we could actually run that calculation. We have the wavelength, we have the period, so we can just divide those. 12 meters divided by 6 seconds tells us that the speed is 12 over 6, 2 meters per second. So that tells us, again, we were saying earlier that a wave is really just a disturbance that propagates outwards through space. This tells us that the disturbance is propagating through space at a speed of 2 meters per second. And so if you watch the wave as it travels, it's going to look like you've got like crests and troughs traveling in some direction. If you watch just one crest as it travels, and of course, really it's the individual pieces of rope moving up and down, but it's going to look like this crest is traveling 2 meters every second, 2 meters forward every second. Any other questions on that so far? Then let's see if we can put all this together into an equation, because I think we have most of the information we need at this point. Our general wave equation bundles all this information together into an equation, a function that can actually be graphed. Since a wave involves both position and time, and the idea is every position at every time has a height associated with it, a displacement. We should be able to write y, the height, as a function of position and time. The idea being we want an equation where if you know a position on the rope and you know what time it is, you should be able to use this equation to predict how high that point is at that time. Since these are clearly sinusoidal functions, I mean, this is the shape we expect from a sine graph, we should write this as a sine function. One thing we need to do though, first of all, this is going to have to involve time and position somehow. Also, if it's just a sine function, what's the highest and lowest the usual default sine function goes?
-1 to 1.
Yeah, sine by default goes down to -1 up to 1. We don't want it to just go down to -1 and up to 1 though. We want it to go up to as high as we want and down to as low as we want. So how can we modify how high and low the graph goes? How can you take that graph? Yeah, if we just multiply by amplitude, a multiplier outside the function takes this graph and stretches it. That allows us to go from, let's say, this graph to this graph. It allows us to stretch the graph or compress the graph vertically. Or by using a multiplier less than 1, we can make it even flatter. So you can adjust this graph to have any amplitude you want by putting a multiplier outside the function. In this case, we know the amplitude is 25 centimeters, so we could fill that in right away. As for what's inside the function, we're going to need to have some way of modifying the time and position. Because time, for instance, by default, time is measured in what units?
In seconds?
Seconds, yeah. The problem is sine function you can't take the sine of 3 seconds. Likewise for x is measured in meters. You can't take the sine of 5 meters. Sine is a function that takes a very specific type of input. If you're taking the sine of something, what sort of units of measurement does it have to be? What sort of thing can you take the sine of?
Radians?
Yeah, it's got to be in radians. It's also possible to use degrees, but radians are going to be much more convenient because sine takes angles as input. If you're taking the sine of something, that only really works if the thing you're taking the sine of is an angle. Time is not an angle, position is not an angle. So what we need to do is multiply by a conversion factor to make this have units of radians. So what we're going to do here, we're going to have sine of something times t. That something is probably best thought of as a conversion factor that turns the time into an angle. Which means we need to cancel out seconds and introduce radians. So we're going to need to multiply by something with radians over seconds. That way, seconds and seconds will cancel out, we'll be left with radians. What's a convenient number of radians to use as just a standard angle? Yeah, 2 pi is really convenient because as an angle, as a rotation, what does 2 pi mean? When we say the radian measure of an angle is 2 pi, how much of an angle is that? Like if I just have some direction and I start rotating, when would I be getting to an angle called 2 pi? 360, that's just another number though. What does that actually mean? What fraction of a rotation is that?
A full rotation?
Yeah, 2 pi or 360 degrees, whatever you want to call it, is 1 full rotation. So if I write 2 pi here, and keep in mind rotation is a cyclic process. If you've got an object that's rotating, it's repeating the same cycle over and over again. 2 pi is 1 full rotation, 1 full cycle worth of angle. What do we call 1 full cycle worth of time? The period, exactly. So this 2 pi over period is effectively a conversion factor. We've got 1 full cycle written as an angle divided by 1 full cycle written as an amount of time. So this acts like just the number 1. We're effectively multiplying the amount of time by a conversion factor to change it from a time to an angle. So this 2 pi over period times time, the result of that is an angle, so we can actually take the sine of it. But it represents an angle that's some specific fraction of a full rotation that corresponds to time as a fraction of a full period. Any questions on that so far? And we can use the same approach with the x term. X also needs to be converted from meters to radians. So we're going to multiply by some number of radians divided by some number of meters. We can still use 2 pi for radians because that's 1 full cycle. But what do we call 1 full cycle worth of distance?
Wavelength.
Yeah, the wavelength, lambda. So 2 pi over wavelength, 2 pi over lambda acts as the conversion factor that turns a distance into an angle, still matching the same fraction of a wavelength or fraction of a cycle, whatever that happens to be. But it converts it into an angle so the sine function can deal with it. And to combine those, we could be adding or subtracting, depending ultimately on what? What do you think is going to determine whether that's plus versus minus?
The energy. Oh, sorry.
The direction, yeah. The plus versus minus here is all about which direction the waves are traveling. And it's sort of a reverse thing here. If the waves are traveling in the positive x direction, we use minus. If they're moving in the negative x direction, we use plus. But it's ultimately all about which direction the wave is actually traveling, which direction the disturbance is propagating through space. Also, we need a couple more things here to adjust the wave, because if we just have this much so far, if we imagine what's going on at, what would be the easiest x and t values to plug in here? Yeah, if we just plug in 0 for both of these, if we're talking about location 0 and time 0, you plug in 0 for x, 0 for t, you get sine of 0. And what is sine of 0? Sine of 0, whether it's radians or degrees, is 0, right? But the thing is, that's not always true for every wave. We don't want to say every wave goes through the origin at time 0. The wave might have a different height at time 0. Maybe at time 0, position 0, the wave is at a maximum, or maybe it's at a minimum, or maybe it's at equilibrium on the way down, or maybe it's somewhere in between. We want to say the initial conditions, the height of the wave at time 0, position 0, could be any height. So to accomplish that, we put an extra plus something inside the sine function, usually written as a Greek lowercase phi. And that's typically called the phase shift or phase constant. Sometimes it was written as phi sub 0, sometimes just phi, but that represents, essentially it represents the initial conditions. The plus phi represents the fact that the wave doesn't have to be going through the origin at time 0. It could have any height at position 0 times 0.
So would this be in terms of like radians too?
Yes.
Like, or would that be on either of the graphs that you have?
It's difficult to tell phi directly from the graphs, but once you have everything else, you can just plug in values from one of the graphs to find phi.
Okay.
For instance, like let's say in this case, we know the period, we know the wavelength, we know the amplitude. Once we figure out everything else, you could just take any point from either graph. Like let's say, for instance, you could say 5 is easy to work with because that's a trough. A max or a min is usually the easiest to work with. You plug in 5 for x, 2 for t, because the whole graph is at t equals 2, and set y equal to 10. And you could solve that for phi, because that phi would be the last unknown. Any questions on that so far? So let's try writing out this equation based on the information we've measured so far.
Is there also like a why not included?
Yes, we are going to need a plus y naught. And why is that? Why can't we just leave the equation as is here?
The origin may be shifted.
Yeah, this equilibrium point specifically is shifted. If you just have this graph as is, the plus phi allows you to shift it left and right. The A allows you to stretch or compress it vertically. The big T and lambda allow you to stretch or compress it horizontally. But it's still going to be centered around 0 as the baseline. It's going to oscillate the same amount above 0 and below 0. It's going to go up to positive A and down to negative A. This one is definitely not oscillating around 0 as a center point. So you can accomplish that by adding something to the wave. If you take the function plus some constant outside the function, that's just going to shift the whole wave up by some amount. So that's what we want to do here. The plus y naught, the plus some constant, allows you to shift the whole graph up or down. And to find that y naught should be the equilibrium value that everything's oscillating around, the average halfway between highest and lowest point. Highest point is 60, lowest point is 10. What's exactly halfway between those?
35.
Right, so that means 35 centimeters in this case would be the y naught, or the equilibrium y value.
So it's the equilibrium position?
Right, it's exactly halfway between the highest y value and lowest y value. I usually think of it as just the height that everything would be at if there was no wave passing through. The average value that everything's oscillating around. Or if you imagine maybe there was some friction involved and the waves gradually got weaker and weaker, then the equilibrium value is the height everything would settle down to after the wave dies out. Any questions on that so far? So let's try writing out that equation with all of the values we have. We've got amplitude is, that was what, 25? Times sine of 2 pi t over, and we found the period was 6 seconds, plus or minus 2 pi x over wavelength, which was 12 meters, plus phi, which I'm going to leave unknown for now, plus y naught, which was 35 centimeters. So this is everything we can get so far just by taking quick measurements from the graphs. Everything beyond that is going to require some further investigation or some calculations. Starting with, the phi is usually the last thing you want to find because that requires knowing everything else first. So let's take a look at the direction of travel. To figure out direction of travel really requires using both of these graphs because anything involving motion is about position and time. So we're going to need to look at the position graph and the time graph in order to make sense of this. And to do that, the position graph, ultimately we want to find a point that they have in common. We want to find a point on the position graph and a point on the time graph that represent the same information, just presented in different ways. We want to know where these cross sections overlap. The position graph, for instance, shows all positions, but only one instant in time. What is that one instant in time?
T equals 2.
What was that?
T equals 2.
Yeah, this whole position graph is this one instant in time, t equals 2. So we look for t equals 2 on the time graph. 2 seconds is this point right here. Likewise, the time graph represents all instants in time, but only one location, x equals 10 meters. So we can look for 10 meters on the position graph, and we get this point right here. So these 2 points really represent the same information. The graphs look different, but this point on the time graph is x equals 10, t equals 2, y equals maybe 55. This point on the position graph is t equals 2, x equals 10, and y equals about 55. So even though these look different, they've got the same numerical coordinates. So they represent the exact same information. Any questions on that so far? So we know that at time 2 seconds and position 10 meters, the rope is, let's say, about 55 centimeters high. And the 55 centimeters in here, I think we could probably interpret Y as distance off the ground. Maybe you're holding the rope some distance off the ground, you're shaking it so that the rope goes as low as 10 centimeters above the ground and as high as 60 centimeters above the ground. But right now, at this position and this time, it's 55 centimeters off the ground. But we don't really care so much where it is now. We want to know what's happening to it. We want to know where's it going next. And keep in mind, this one location, this one piece of rope isn't moving left or right at all. The wave itself, the disturbance is propagating to the left or right, but this point on the rope is only oscillating up and down. So our only options are, is it moving up or is it moving down? Which graph should we look at if we want to know what's happening next, whether it's on its way up or on its way down?
Would it be the time one?
Yeah, the time graph is perfect if we want to know what happens next, because what happens next means a little forward into the future. That's traveling forward in time. Because keep in mind, on the position graph, left and right on the position graph actually represent left and right in space, or forward and backward if you want to call it that. For the time graph though, left and right don't actually mean left and right. To the left on the time graph means into the past, to the right on the time graph means into the future. So don't think of this as left and right or forward and backward. Think of this as into the past and into the future, because this is an axis representing time. So if we want to know what happens next, let's project this a little forward into the future. As we go into the future, is this point on its way up or on its way down?
Up?
Yes, this is on its way up. The positive slope guarantees that. Going into the future means going up in this context. So we know that at this time and this position, that piece of rope is 55 centimeters high and on its way up as time passes. Now, if we take that information with us back to the position graph, we know this point is on its way up. Now our next goal is to figure out which direction the wave itself is traveling, not the point. We know the point is just bobbing up and down and is currently on its way up. We want to know which direction the wave itself is traveling. Is the wave shifting to the right or is the wave shifting to the left in order to make this point go up? So if we have the wave, and I find it's often useful to just like shape your hands in the shape of the wave near that point. Should that wave shift to the left or shift to the right to make this point go up?
I'm sorry. So when we're shifting it, are we just shifting the whole graph?
Yeah, if you imagine this graph is animated, the wave itself, the shape of the graph, this curve is shifting either to the left or shifting to the right.
Oh, okay.
If we actually try both of those, like let's say we allow the wave to go a little bit to the right. So if you imagine every point goes a little bit to the right, the wave now looks like this. Has that allowed this point to go up or down? Yeah, location, because remember, we're keeping the same x value. We're keeping x equals 2, or sorry, x equals 10. If the curve has shifted to the right, then location x equals 10 has gone down. But we don't want that. We want location x equals 10 to go up. So shifting to the right doesn't work. Instead, we're going to have to shift the graph to the left. If you shift every point a little bit to the left, the graph now looks like this, the green curve here. Every point a little bit to the left. And now this point at x equals 10 has moved up. So the graph shifting to the left is actually what works here. It causes the point to move up. You might also find it useful to think of this in terms of the nearest crest versus the nearest trough. If we want this point to move up, should a crest or a trough be moving towards it? Yeah, got to be a crest. If we want this point to move up, the only way for that to happen is if the nearest crest moved towards it. The nearest crest to x equals 10 is this one right here. So we should expect this crest to move towards location x equals 10. That means the crest at, looks like a crest at 11. The crest at 11 has to move to the left to get to x equals 10. So we know the wave is moving to the left here. In other words, the negative x direction. So this wave is moving to the left, this wave is moving in the negative x direction. And that tells us what to use for the sign here. If the wave is moving in the negative x direction, what sign should we use in the equation? Yeah, we're gonna have to use plus here. So this is specifically plus. And at this point, we now have every piece of information we need except for what? What's the one missing parameter here? Yeah, we still need to find the value of phi. And for phi, since we have everything else, if we can just fill in an x value and a t value, and perhaps a y value, which we can get from any point on either graph, then phi is the only unknown left. So we just need to choose any point on either graph. Although to avoid ambiguity, a crest or a trough is best because there's only one crest in each cycle, there's only one trough in each cycle. So that's unique. If you choose another location, like let's say an equilibrium point, equilibrium shows up twice in each cycle. So that leads to some ambiguity and you don't want to have to worry about that. So let's choose a single crest or trough. What would be some coordinates of a crest or a trough that we can easily identify? Just give me an x value or a t value that seems to be definitely a crest or definitely a trough.
T value 2.5.
Yeah, it looks like 2.5 as the value of t. That is very definitely a crest. We've got a crest, in other words, a maximum y value at t equals 2.5 seconds. And x equals 10 because this entire graph is x equals 10. So we could plug in 2.5 for t, 10 for x, and set y equal to the maximum value, 60. And then solve for phi. But a faster way to do this, instead of looking at the entire equation, we can focus on just what's inside the sine function, which is called the total phase. Total phase just means everything inside the sine function. That's usually written as a capital phi. So that's 2 pi t over 6 seconds plus 2 pi x over 12 meters plus this unknown phase shift. We can plug in the values we've got. T is 2.5. And the seconds are going to cancel out. X is 10, and the meters are going to cancel out. And since we're at a crest, what input could you use for sine to get the maximum value? What angle has sine of that angle being the highest possible? Right, pi over 2. If you're at a crest, the total phase should be pi over 2. Or if you're at a trough, the total phase should be 3 pi over 2, or negative pi over 2, either way works. But total phase is a very useful way of standardizing information about what type of point we're looking at. If you're looking at a crest, you have total phase equals pi over 2. If you're looking at a trough, you have total phase equals 3 pi over 2. If you're at equilibrium, total phase might be pi or 0, depending on which equilibrium you're at. So that's the ambiguity we want to avoid. But a crest or a trough makes total phase very predictable. At this point, you could solve for phi. Just simplify both of these, subtract it from both sides, and you get a value for phi in radians. Plug that into your original equation, and that is the wave equation for these graphs. Any questions on that? And if you want to get some more practice on this, I've got a worksheet of more wave graphs at mathandcheese.org. If you just go to math.andcheese.org/P7C, put that in the chat. That should have a worksheet on waves along the lines of, here's some graphs, find the equations. So give that a try if you want some more practice. Feel free to email me if you want to request any topics for next time, and I will see you later.